Few NATO intelligence analysts could peek behind the Iron Curtain and live to tell the tale. The Soviet Union treated its naval secrets like the crown jewels, tightly controlled and fiercely guarded. Nevertheless, CIA operatives and other Western intelligence collectors maintained a steady, risky pattern of surveillance, listening posts, human assets, aerial reconnaissance, and clandestine riverine observations, and they funneled the fragments they gathered into analytical reports for the Pentagon and allied partners. In mid-1969, a small team on a routine reconnaissance along the Neva River in Leningrad noticed something unusual at the old Sudomekh submarine shipyard, a compact, modern submarine moored alongside older, bulkier vessels. At first glance, its silhouette looked familiar, but a closer look revealed a startling combination of features. It stretched more than 79 meters, boasted an unusually sleek hydrodynamic hull, and, most disconcerting to the observers, its outer skin glinted like polished metal in the pale northern light. That high gloss suggested the use of a novel material or finish, not the dull matte paint common to Soviet hulls of the era. Analysts back in Washington pored over the photographs and eyewitness testimony. The more they cross-checked measurements and acoustic intelligence, the clearer a worrying picture became. The Soviets had not simply modified an existing design. They appeared to have created a completely new class of submarine whose primary structure relied heavily on titanium alloy. Titanium's exceptional strength-to-weight ratio and superior corrosion resistance promised a hull lighter than comparable steel designs, yet far stronger under pressure, potentially allowing higher speeds, deeper diving depths, and a lower acoustic signature. For U.S. naval planners and weapons designers, this presented a pernicious conundrum. Torpedoes and countermeasures developed to defeat steel-hulled boats might lack both the energy transfer and the terminal effects necessary against a titanium structure. The intelligence community's nickname for the mysterious craft, the Golden Fish, captured both its reflective sheen and the unease it inspired. To understand the broader significance, you have to look at the Soviet Navy's transformation across mid-century decades. After the Russian Civil War and through World War II, the Soviet naval effort had been largely defensive and regionally focused, tasked with protecting coastal waters and convoy routes from enemy surface ships and submarines. The wartime experience exposed glaring gaps in technology and operational doctrine, but the post-war geopolitical settlement and the onset of the Cold War created incentives and resources for a different ambition: to build a navy that could project power far from Soviet shores. The nuclear age accelerated that effort. The United States moved aggressively into nuclear propulsion and ballistic missile submarines, upending naval strategy by creating a survivable, sea-based strategic deterrent. The Soviet leadership, determined not to cede that dimension of power, directed enormous state resources to close the gap, sometimes by producing enormous numbers of conventional platforms, sometimes by pursuing radical technological leaps that could leapfrog Western advantages. Throughout the 1950s and early 1960s, the Soviet design bureaus and the Central Committee issued a string of directives aimed at modernizing and diversifying submarine capabilities. Rather than copy a single Western model, Moscow authorized multiple, parallel projects, some focused on anti-ship guided missile boats, others on torpedo-armed attack submarines, and some on experimental designs pushing the frontier of submerged speed and stealth. Projects 661, later dubbed the Papa class by NATO, and Projects 651 and 659, Juliet and Echo in NATO parlance, each represented different trade-offs between speed, armament, and endurance. Project 705, however, set out to be fundamentally disruptive. It called for a small, fast interceptor, a submersible specifically designed to dash under Arctic ice or across the North Atlantic, burst at exceptionally high speeds to threaten carrier formations, then vanish before traditional ASW, anti-submarine, warfare forces could respond. The engineering challenges Project 705 posed were immense. To reach the targeted 40-knot speeds underwater, a conventional steel-hulled vessel would be hamstrung by weight and hydrodynamic drag. Achieving the same burst speed with a small displacement required radical reductions in hull thickness and weight without sacrificing structural integrity. Titanium presented an elegant theoretical solution. At the same time, however, titanium is notoriously difficult to work with. It demands specialized alloys, precise metallurgical control, new welding techniques, and fabrication facilities that can operate in inert atmospheres to avoid contamination. Soviet industry had ample experience with steel and aluminum shipbuilding, but large-scale titanium construction required investments in new furnaces, machining centers, non-standard tooling, and extensive personnel retraining. These bottlenecks ensured the project would be costly, time-consuming, and technically risky. Design work accelerated after M.G. Rusinov and other engineers sketched out promising concepts in the late 1950s. By 1960, the SKB-143 Design Bureau in Leningrad had been assigned to take the rough concept into a detailed engineering program. Across the next several years, the design was iterated relentlessly. Hydrodynamicists tested hull shapes in towing tanks, acoustic engineers chased ways to reduce noise from pumps and machinery, and designers reorganized internal spaces to allow a radically smaller crew. The goal was not just raw speed, but survivability. Lower detectability through reduced acoustic, magnetic, and thermal signatures was as important as a high surface or submerged dash speed. Specialists evaluated propulsion choices, including compact, high-power turbines, and novel propulsors, while system engineers fussed over life support, weapon integration, and emergency escape systems for a cramped vessel with minimal redundancy. By 1963, practical realities forced several significant design adjustments. Initial displacement targets of roughly 1,500 tons were deemed too optimistic when balanced against structural safety margins and the need for onboard systems. Displacement grew to around 2,300 tons. Designers doubled internal compartmentation to 6 separate sections to improve survivability after collisions or combat damage, and crew complements were capped around 29 to preserve compactness while still allowing around-the-clock operations. The trade-offs extended into habitability and logistics. A small crew meant automation had to shoulder more duties, but it also required an unprecedented degree of reliability from pumps, control systems, and propulsion gear in an era before modern digital control. Beyond the metallurgy and machinery, Project 705 represented a broader Soviet risk calculus. Instead of mass-producing slightly improved versions of existing boats, they would invest in a high-tech, specialized asset that might alter NATO operational planning. If the Alpha-class submarine could operate at high speed with a low acoustic footprint and the ability to operate under polar ice, it could hold carrier battle groups at risk in theaters previously thought secure. Conversely, failure would mean years of sunk cost and valuable engineering lessons that might only indirectly inform later, more conservative designs. Production officially began in 1964 in Leningrad, where the workshops and new titanium-capable facilities labored under secrecy and intense pressure. The lead hull, designated K-64, worked its way through trials and modifications for years and was finally commissioned in 1971, entering service amid fanfare, concern, and a rapidly changing naval environment. In service, the Alpha class delivered both promise and problems. Its blistering speed and unique titanium construction gained it a fearsome reputation, but operational realities, high maintenance demands, complex reactor and propulsion issues, and the stresses of titanium fabrication meant the class was expensive to run and required specialized dockyard support. Still, the project's legacy went beyond a single hull type. It pushed Soviet metallurgy, shipbuilding techniques, and marine engineering forward, produced new tactical doctrines for high-speed interception and under-ice operations, and forced NATO navies to rethink anti-submarine tactics and weaponry to cope with a platform that did not fit neatly into established threat models. The tale of the golden fish thus sits at the intersection of industrial daring, strategic necessity, and the Cold War's relentless competition for technological advantage. During these years, undercover American intelligence agents maintained a close, often dangerous watch on Soviet progress in the program, running a mosaic of human intelligence, reconnaissance flights, signals intercepts, and clandestine riverine observations to piece together a picture that Moscow wanted to keep secret. In late 1969, a routine patrol along the Neva River produced a striking discovery. Docked among older, familiar hulls at the Sudomekh shipyard in Leningrad lay a compact, modern submarine, unlike anything Western observers had seen. Senior Submarine. Analyst Herb Lord and other specialists quickly realized this was not a mere modification of an existing design, but a purpose-built nuclear-powered attack submarine with an array of novel features. Initial on-site estimates from CIA operatives and naval engineers put its length at roughly 80 meters, a surface displacement near 2,600 tons, and a submerged displacement on the order of 3,700 tons, dimensions that made the boat unusually small for a nuclear attack submarine, yet denser in capability. Observers noted a streamlined, almost sculpted hull form and calculated an unusually high reserve buoyancy of around 30%, a figure that contrasted sharply with the 8 to 11% common to contemporary U.S. Navy boats. Such excess buoyancy hinted at design choices favoring rapid surfacing, safety margins, and hydrodynamic efficiency. Equally remarkable was the hull's sheen. In certain light it looked polished, reflective, and not the dull, dark finish typical of Soviet tonnage, which led analysts to suspect the use of non-standard materials. Within weeks, the intelligence community reached the conclusion that this was a ground-up development, and NATO quickly assigned the reporting name Alpha Class SSN. As CIA reporting matured, technical analysts cross-referenced imagery, acoustic signatures, and shipyard procurement indicators, and became increasingly confident that the Soviets had employed a titanium alloy in the pressure hull. Project 705, as the design was known in Soviet documentation, used a double hull arrangement in which the inner load-bearing pressure hull was complemented by an outer hydrodynamic casing. Titanium's higher strength-to-weight ratio allowed the inner hull to be both lighter and materially tougher than comparable steel sections, reducing overall displacement for a given pressure tolerance and enabling greater operating depth and resistance to near-miss explosive shock. Because titanium is effectively non-magnetic, the Alpha class was also less susceptible to magnetic anomaly detection and certain types of mine triggers that relied on ferrous signatures, complicating the task of NATO anti-submarine warfare units. The material's downside was its cost and the industrial challenge of working it. Titanium ran roughly 3 times the expense of shipbuilding steel and demanded specialized fabrication techniques. Project 705's designers pursued extreme automation to shrink crew size and increase system responsiveness. The pressure hull was divided into 6 watertight compartments, but only one, typically the third, was continuously manned. The remaining sections ran primarily on automated systems that required periodic inspection or maintenance by a core crew of roughly 16 to 20 sailors, a dramatic departure from the 120-160 personnel typical of other nuclear attack boats of the era. This compression of manpower had operational consequences. A smaller crew reduced life support, provisions and accommodation demands, but placed heavy reliance on machine reliability and centralized control. Automation shortened the chain of command, enabling faster decision loops in combat but amplifying vulnerability to single-point failures. Designers mitigated that risk through redundancy in critical systems and compartmentalized control networks. Reduced crew size also meant less onboard human noise, fewer boots on deck, fewer mechanical disturbances, marginally aiding acoustic stealth, though it made damage control and extended missions more challenging without a larger maintenance cadre. Propulsion and maneuvering systems on the Alpha class reflected the same compact, high-power priorities. Designers explored compact reactor plant layouts and powerful, lightweight turbines coupled with advanced propulsors to achieve burst speeds far beyond typical attack submarines. High-speed capability was central to the ship's intended role. Sprint across the Arctic or North Atlantic to intercept carrier battle groups, deploy torpedoes or missiles in fleeting windows, and then dash away beneath thermal layers or under ice. Achieving such speeds in a small displacement hull demanded careful attention to cavitation control, pump and turbine isolation, and noise damping for auxiliary machinery so that the boat could accelerate without immediately broadcasting its presence. Acoustic engineers and machinists spent years refining mountings, fluid dynamics, and propulsor geometry to minimize the telltale signature that would otherwise betray a high-speed dash. Operational doctrine for the Alpha class emphasized short, violent patrol profiles rather than long-endurance loitering. Their missions anticipated high-risk intercepts, rapid ingress, and egress under polar ice or in confined sea lanes, and the need to function with minimal external support. That operational concept shaped onboard systems: compact but lethal torpedo armament, rapid-fire control loops, high-capacity compressors for emergency surfacing, and a suite of sensors tuned for quick high-confidence target classification. Limited habitability was a trade-off. Missions tended to be shorter or more episodic, with Alpha boats often returning to specialized bases for refit and maintenance, rather than operating on the long patrol rotations, typical of larger nuclear submarines. Secrecy and industrial strain were constant companions of the program. Producing large titanium sections required new furnaces, cleanroom welding processes, inert gas handling to prevent contamination, and retraining thousands of welders and machinists. Dockyards capable of servicing the Alpha class needed specialized tooling and protocols. Even routine repairs demanded highly trained technicians and, in many cases, facilities that only a few yards in the Soviet Union possessed. These constraints meant that while the Alpha was a leap forward in metallurgy and performance, it was also expensive to maintain, logistically brittle and difficult to field in large numbers. Western navies watched nervously as intelligence estimates refined the Alpha's capabilities. Naval planners studied the implications for convoy defense, carrier protection and under-ice operations, and weapons designers revisited torpedo warhead designs, propulsion power and guidance logic in an attempt to ensure terminal effectiveness against tougher titanium structures. Anti-submarine tactics were adjusted, greater emphasis on multi-platform detection, sonobuoys, maritime patrol aircraft, hunter-killer groups, development of higher-energy interceptors, and experiments with standoff weapons that could deliver more destructive energy profiles. Military scientists also explored novel detection avenues, including finer-grained acoustic processing, non-acoustic sensors, and techniques to exploit the Alpha's thermal or hydrodynamic signatures. The human dimension of the Alpha-class story was complex. Crews lived and worked in exceptionally cramped conditions, subject to high levels of acceleration, noise, and stress during the kind of high-speed maneuvers the boats were designed for. Training programs became more intense and specialized, focusing on automation oversight, rapid damage assessment, and recovery procedures that differed from the culture of larger, more redundant submarines. Sailors prized the Alpha's speed and capability, but also faced the reality that its maintenance and operational tempo made it a demanding platform to serve on. In strategic terms, Project 705 embodied the Soviet willingness to take concentrated technological risks to offset Western advantages. It pushed forward Soviet metallurgy, fabrication techniques, and naval doctrine while forcing NATO to broaden its ASW toolkit. At the same time, the program highlighted the limits of high-tech specialization. Titanium hulls and radical automation delivered impressive performance, but at the cost of expense, maintainability, and scale. The intelligence gathered by those early riverine observers and the months of analysis that followed transformed how planners on both sides understood the underwater battlefield and set in motion a series of technical and tactical responses that would shape Cold War naval competition for years to come. The Alpha's engineering program pushed several technologies to extremes in pursuit of a new type of undersea weapon, compact, fast, and difficult to detect. Central to that effort was the choice of a liquid metal-cooled reactor, most often using a lead-bismuth eutectic in Soviet practice, which offered very high heat transfer, a compact core size, and lower coolant flow requirements compared with pressurized water reactors. The result was a reactor plant that could deliver an unusually favorable horsepower to weight and volume ratio, allowing designers to pack more power into a smaller hull and enabling the short, high-speed bursts the submarine was expected to perform. Those same choices, however, created maintenance headaches. Liquid metal coolants solidify at modest temperatures, complicating cold startups and maintenance work, and they required specialized handling, decontamination, and repair facilities that constrained deployment flexibility. The Alpha integrated a level of electronic automation rare for submarines of its day. An onboard combat information and control system fused radar returns, inertial and celestial navigation inputs, low-light television feeds, and hydroacoustic data into a consolidated tactical picture. The aim was to reduce operator load, shorten sensor-to-shooter timelines, and permit a very small crew to handle situational awareness tasks that once required entire compartments of sailors. The weapon control suite automated target tracking, fire control calculations, and torpedo guidance handoffs so that engagement sequences could be executed in seconds. A separate automated hydroacoustic processor continuously scanned for contacts and fed pre-filtered ranked targets into the combat system, minimizing the need for manual acoustic plotters and freeing watchstanders to supervise rather than toil. That automation, combined with an architecture that separated detection, command and weapons functions into discrete redundant modules, was the key enabler for the Alpha's tiny crew and fast reaction doctrine. Armament and mission fit reflected the boat's interceptor concept. The Alpha carried lightweight torpedoes designed for quick acquisition and short-range lethal effect, anti-ship cruise missiles for standoff engagement, and mines for area denial. Designers accepted limited payload volume in exchange for a high-speed interception envelope and rapid reload recovery cycles. Torpedo types and missile packages emphasized compact size, rapid lock-on, and high-speed performance to match the Alpha's tactical profile. The boat's sensors and fire control logic were tuned for decisive, high-confidence engagements, rather than protracted cat-and-mouse hunts. In practice, this meant a doctrine of fast approach, quick engagement, and rapid egress before coordinated ASW assets could localize and prosecute the contact. Hull and signature management received extraordinary attention. The titanium pressure hull allowed higher depth ratings and provided greater structural resilience to explosive shock and pressure cycling. But the design team also worked hard to suppress non-structural signatures. Machinery mounts were carefully engineered to isolate vibrational energy. Hydraulic pumps were redesigned for low cavitation flow, and auxiliary systems were clustered and acoustically baffled to prevent small noises from becoming telltale clues at range. Thermal management systems were optimized so that the Alpha's waste heat and cooling plumes were minimized, and the boat's external shape and propulsor geometry were refined to reduce cavitation at high speed. The end result was a platform that, for short periods while sprinting, could be acoustically and magnetically elusive in ways that complicated established NATO detection techniques. The industrial and logistical footprint required to build and sustain the class was considerable. Titanium fabrication demanded inert atmosphere welding cells, new forging processes, and quality control regimes that monitored microstructure and contamination at every stage. Workers had to learn different handling, cutting, and inspection processes compared with steel. Reactor and propulsion shops required specialized tooling to safely service liquid metal systems, and bases that hosted Alphas needed dry docks with titanium-compatible facilities. Argon systems and teams trained in non-ferrous repairs. Those requirements concentrated Alpha operations at a handful of specialized yards and bases, effectively reducing the strategic flexibility that mass-producible designs enjoyed. Western technical and operational communities reacted to the Alpha program by rethinking the balance of weapons, sensors, and tactics. The emergence of a small, fast, harder-to-damage target encouraged investments in higher-energy torpedoes, improved guidance algorithms, and new approaches to detection that combined multiple sensing modalities. The U.S. Mark 48 and Britain's Spearfish, developed in the decades around the Alpha's entry into service, reflected a shift toward heavier, more capable homing weapons with longer range, greater speed, and more powerful warheads, explicitly intended to close the damage gap against tougher hulls and to defeat fast-evading targets. ASW practice increasingly emphasized layered detection, acoustic, non-acoustic, airborne and satellite-based, and coordinated prosecution so that a single fast attacker could be engaged by simultaneous, cross-domain assets before it could exploit its speed advantage. Human factors were a recurring constraint in Alpha operations. Crews faced cramped quarters, a high operational tempo, and the physiological strains of repeated high-speed maneuvers and deep dives. Automation reduced some routine burden but increased the demand for a crew capable of systems oversight, rapid diagnostic intervention, and specialized maintenance. Training pipelines adapted. Sailors spent more time in simulators, practiced emergency procedures for liquid metal reactor incidents, and drilled for high-intensity, short-duration mission profiles rather than extended patrol endurance. The combination of higher maintenance costs, a small pool of suitably trained personnel, and complex logistics meant the class required disproportionate state resources relative to its numbers. Politically and strategically, the Alpha story was mixed. On one hand, it was proof that concentrated investment and technological daring could produce platforms that complicated NATO planning and pushed ASW technology forward. On the other hand, it illustrated the perils of highly specialized weapon systems. Cost, sustainment complexity, and limited operational flexibility constrained how widely such boats could be employed. By the time geopolitical winds changed and budget pressures mounted, Alphas were expensive to maintain and field. The class had to be retired earlier than simpler, more versatile designs might have been. Yet the technological advances the program forced, titanium metallurgy, high-speed hydrodynamics, automation for minimal crews and lessons in liquid metal reactor handling, left a durable legacy in subsequent Soviet and Russian submarine designs, naval engineering practices, and Western countermeasures strategies.